extreme weather here at the South. He did his undergrad at Open University and then his master's and PhD with Colin Price in Tel Aviv University and a postdoc at Yale University. And his fields of interest are space weather, atmospheric electricity, and their interference thing, and climate change. He will tell more about himself. Thanks for being here.
Okay, thank you very much. So this is my second lecture over here, and I happy to see you all. Thanks, Aviv, for introducing me. I will say a little bit about myself, but I am one of yours. And so I work over here in the lab managers and the scientists in the laboratory of extreme weather and predictability with Dr. Asaf Ochman and the students. And this is part of the things that I'm doing. I am also working as a senior scientist in the Center for Climate Health and Human Health in the Shiva Tel Shomer. And I want to talk to you about the impact of space weather on the atmosphere over Israel. I think that last year I spoke about ground measurements of electric fields, and now I want to talk about some of the airborne measurements that we did. And I want to talk about I want to summarize the ground measurement that I spoke last year for the new students, and also add a new paper that was published in 2023. So I will begin. The layout of my talk would be airborne measurement using meteorological balloons. You can see me over here holding this nice flex balloon. Then I will talk about some of the ground measurements, a summary of the ground measurements, and the non-effect of space weather at the ground level in Israel. And then I will summarize everything. So, several years ago, we did an air balloon campaign using meteorological balloons, and we began to launch them with a spatial payload. The payload consisted, it's like a radio sound, but we made some changes to the radio sound. So beside the sensors that you see over here, that some of them measure the temperature, the relative humidity, and the pressure, we inserted also a Geiger counter. The Geiger counter was inserted to measure the ionization rate, which is dependent on the altitude. Now, a Geiger counter is like a sealed tube with a gas inside. And when particles interact with the gas inside, simply what they are doing is they are like pushing an electron away from the gas atom. Then the electron is diverted into an electrode, and electrical current is being counted. So this is a Geiger counter. He's counting the electrical signal. I want to show you also a nice movie. It's a very long movie, but we'll show you several minutes. So this is how our land is looking from above. Transmitting video is not something easy. We did it only once because you see there are a lot of disturbances when transmitting from quite high altitudes. We are speaking about our balloon exploded around 35 kilometers. Typically from, there were some that exploded around 20, but some exploded around 35. So transmitting video is it's It's not that easy. And another problem with launching a balloon is that it spins a lot. So you see that the video also spins, so it's not something easy to do. There is a solution that may help us to balance the balloons, but again, it spins and it also rotates a little bit. So it's not something that is very easy. This balloon launch was from Ariel University in Samaria region, but most of the balloon launches that we did were from the Negev desert, from Mitzpe Ramon. So a little bit of a brief introduction about ionization in the upper atmosphere and the vertical profile of ionization, because the balloon is going up and measures the ionization as a function of the altitude. A German scientist in 1912 named Haas investigated the vertical ionization profile. And what they thought prior to his experiments is that the main source of ionization is from the ground, from the earth. Radioactive decay from the radioactive decay chains that are producing gamma rays that ionize the atmosphere near the ground. Now the main idea is when we go further away from the ground, the ionization will decrease. So this was the assumption. And they did their experiment, and they found out that no, ionization didn't decrease as we go further from the ground. Ionization increased as we go up the atmosphere. Then there should be a source to this ionization. And the source is from outer space. So this is how the galactic cosmic rays were found. And the galactic cosmic rays are flux of energetic particles that are coming from all around us, especially and typically from remnants of supernovas that wash the solar system, and they penetrate into the Earth's atmosphere and interact with the atmosphere.
What's the unit on the Earth?
Ionization effect.
What is it?
The ionization count rate. Okay?
It's the number of electrons produced per what?
Per minute.
Per minute?
Yes.
In a cubic meter? Or cubic? What?
When the Geiger counter goes up and measures, then it measures number of counts
in a
per minute. Yes,
Oh,
in the tube.
And there is a standard size of the tube?
It's a small one.
But if you increase
If you get a bigger one,
the
then
numbers will be different.
So this is the ionization effect as a function of the altitude. And we see over here that there is a maximum of the ionization around 20 kilometers. This is called the Regner-Fotzer maximum. The average is around between 70 and 20. Now, both of them were Germans. This one, Regner, was married to a Russian Jewish lady. And because he was married to a Russian Jewish lady, and the German regime, prior to World War II, asked him to divorce her. And because he didn't wanted to divorce his wife, then they decided to drop his name from the papers, and it was was called for a lot of time only Fotzer maximum. Later on, everything was corrected, and now it's called regular Fotzer maximum. So the maximum interaction of the atmosphere of the galactic cosmic race is around here, but why? Because above that altitude, the atmosphere is too diluted. It's too thin. So there's less interaction. Below it, the particles are not so energetic to penetrate deep enough to the atmosphere. So we get the in-between. Over here, we have the maximum interaction. And both of them found it out. So it's called regular Fotzer maximum. So we did the same. We wanted to check for the first time above Israel, where do we find the regular Fotzer maximum? Do we see it also? So we used balloon launches with a Geiger counter. We published a paper on this in 2016. And what we did is an airborne balloon campaign to measure the ionization. And later with a simple calculation, I also calculated the radiation dose rate, and I will explain it later. We wanted to find the solar impact of ionization. Now, we did the balloon campaign from 2014 till 2016. It was during the phase of the solar cycle from solar minimum to the solar maximum. Several years between the solar minimum to the solar maximum, and we wanted to see if there is an effect of the solar cycle, at least part of it.
Sunspot?
Yeah, the sunspot is something that can tell us something about the solar activity. So if we have a lot of sunspot, then the sun is very active, and when there are little sunspots, the sunspot number is very low, then the solar activity is low. And there is a 11 years cycle. So the first launch was in 2014, the last launch was in 2016. Some of them we measured also during descent. Most of them were in Assen when the balloon went up. Then it exploded. So later on we decided to tie a parachute to the balloon. Then when it goes down, it will measure as well. And you see that these launches that we published in the paper were taken from Mitzpe Ramon. Some of them landed in Israel, but some of them even landed in Jordan. Later on, we did some other launches, and we had a very strong wind in the stratosphere to the east. It is not recorded on this map, but the balloon arrived to the border between Jordan and Iraq. And it had a camera, and because it had a parachute, the camera kept broadcasting to us. Then we saw someone pick it up and then probably dismembered it, and I don't know what they did with it. But according to the latitude and longitude, it's landed near Iraq. Probably thought it Spinoza or something. I don't know. So we wanted to find the solar impact on the ionization. We wanted to find the latitude dependence. So everything was launched from Mitzpe Ramon, but we did a simultaneous experiment where we launched from Mitzpe Ramon from Spain and from the UK as well. Why? I will explain later. Then we wanted to find the radiation dose rate, because if the balloon that measures the ionization pass the tropopause and 10 kilometers, then we can measure the dose rate where the commercial lines are flying. And we measured also the meteorological parameters, so we can see the pressure profile above Israel and the temperature profile above Israel. In black we see a standard average atmosphere profile, and the colors represent the different temperature profile for each date. So you can see that it quite fits well, but you can see that the atmosphere, for example, the minimum temperature above Israel at the altitude of between 15 and 20 kilometers can reach minus 80 degrees Celsius compared to the minus 60 of the standard atmosphere. The pressure profile looks quite the same. Beside temperature and pressure, we measured also the relative humidity profile above Israel. We can see that over here till 10 kilometers there are variations in the relative humidity, like the red one from May 2015. We did see the balloon passing through an observable cumulus cloud, and we see the increase to almost 90% of relative humidity, and then decreasing back to very low values. The green one in 2014, October 2014, we saw that there was an observable cirrus layer also, and then we see an increase in the relative humidity for approximately, let's say, 2-3 kilometers. So this is the width of the layer, and then it's decreasing again, and above 20 kilometers, we see that the relative humidity is almost zero. As for the ionization profile, so we got something that is quite similar to past results. So we have the ionization and the altitude, and we see that the average ionization rate from all the experiments that we did shows that the maximum ionization, the average of this, is between 15 to 20 kilometers, which is quite agreeing with the past results of the Regner-Fotzer maximum. So I decided to do it, instead of altitude and ionization, I decided to plot the image of ionization against pressure, so I'll be able to compare it to past measurements. So I plotted the ionization. The x-axis is the pressure in millibar, and again we see that the maximum of ionization of all the experiments that we did lies around 20 kilometers, which is the 100 millibar pressure. And if we compare it to past results from a V2 rocket that was fired by the Germans and was published by Israel in 2017, we see that the height is completely the same. But the ionization rate is much higher. We see that ionization over here reached a maximum of 35 to 40 counts per minute. And over here we have ionization of counts per second of 150, but this is at the UK, which means very, very high latitude compared to the low latitude at our place, also at Germany. The next thing that we did is to understand the latitude dependence. And the latitude dependence, because we are talking about the galactic cosmic rays. And now we need to understand that the magnetospheric shielding, the magnetosphere, is shielding our atmosphere from charged particles to enter deeper into the atmosphere. The geomagnetic latitude is a parameter which is defined by latitude cutoff rigidity. It is a concept that describes the geomagnetic shielding by the magnetosphere against the arrival of charged cosmic ray particles. So everyone knows what charged particles and how they interact with the magnetic shield. Okay, and you all remember, I think, this is what we are doing, right? The velocity of the particle, the magnetic field and the force that is acting on the particles. Most of them are diverted into the polar caps. Particles cannot penetrate to locations with the geomagnetic cutoff greater than the particle's rigidity, which means that only the strong particles can penetrate. So we did some model results using a Monte Carlo model to check the latitude dependence between three places: Israel, Spain, and the United Kingdom. So we see over here the altitude as a function of the ionization rate, and we see that low ionization rate is because the magnetic shielding of the magnetosphere is the highest. High ionization rate, meaning more particles are interacting with the atmosphere, is due to the reason that the magnetospheric shielding is lower at higher altitude. So this is the model results. So we did an experiment. It was almost simultaneously due to regulations. The Spanish team successfully made the launch 2 days after, but it's approximate. It's good enough. And we see the same results. The Geiger count rates, 3 identical systems with a Geiger tube launched from Israel, Spain, and the UK, and we see that the count rate is the lowest in Israel and the highest in the UK, and Spain is in between.
The numbers are.
What?
The numbers are very different.
Yes.
It's different units.
This is ionization rate. Okay, and this is the count rate. Did you want to say something?
Yeah, I just wanted to ask, so the rigidity is to penetration to lower latitudes from the North Pole? I didn't understand the concept of rigidity. That's,
it's dependent on the latitude. It depends on the latitude. Then the last step was with a simple calculation that is found in the literature to convert the ionization rate and the count rate that you are measured into exposure. So this is the radiation dose rate. So we took, I took the ionization rate, which was dependent on the altitude, and I converted it to the radiation dose rate in the units are millisievert per hour. And over here I placed the tropopause because quite close to the tropopause it's where the commercial airlines are flying. Now the FAA, the US Federal Aviation Administration, reports in the literature that the dose rate from galactic cosmic rays, the average, is around 6 millisievert per hour for common domestic US air travel. At 10.6 kilometers, we got around 3.5. So it's reasonable because it's a lower latitude. At the equator, where the magnetospheric shielding is at the maximum, at the altitude of 12.2 kilometers, it's even lower. Then what I did is to take the dose rate at 10 kilometers for each. So I took the dose rate at 10 kilometers for each of the flights from 2014 and 2016, and then I plotted it against the sunspot number. And what we see over here, that the dose rate is increasing when the sunspot number is getting low. And why is that? Because when the solar activity is very, very high, when the sunspot number is very high, then the solar activity is very high. And when the solar activity is very high, the magnetic fields produced by our sun prevent from the galactic rays to penetrate into the solar system. When the sunspot observes that the sun is very, very low, then the solar activity is very low, meaning the magnetic fields produced by our sun do not prevent the galactic cosmic rays arriving from the cosmos into our solar system. So a lot of galactic cosmic rays arriving to our solar system because the magnetosphere shielding of our sun is lower. That is why more galactic cosmic rays penetrate the sun magnetosphere and penetrate the Earth magnetosphere, and this is why the dose rate is going up and the ionization rate is going up. So that was the airborne measurement and some of the results. How much time do I have? I have time. Okay. So this is enough to complete the ground measurement. This is an electric field meter that is placed, which I built, that is built in Mitzpe Ramon in Israel. I built another one like this in Ariel University and another one on top of the Hermon mountain. Sadly, we can't go over there. Hopefully we will build more in the future. So it's measured the electric field at 3 meters high. Typical electric field at 3 meters high is around, the average is around 130 volts per meter. Okay. A brief introduction. The global electrical circuit. So it's an electrical circuit. For electrical circuit, you need two things. You need the charge and you need the batteries. The batteries are the thunderstorms. Okay? The thunderstorms in the extreme weather region. We have two conductive plates. The upper conductive plate is the ionosphere, an ionizing layer which is ionized by the sun, between 60 to 100 kilometers. It depends if it is the day side or the night.
D&E.
Yes.
D&E layers?
Yes.
D&E.
It is numbered with Latin letters. The lower conductive plate is the Earth ground because the ground is conductive. So this is the circle. The potential difference between the two plates is between 300 and 350 kilovolt. Okay? You know that, I hope that some of the students know what is the potential difference. For example, the battery over here is 1.5 volt. Okay? So it's 350,000 volts. The current returned back to Earth in the fair weather region, what we have right now, nice blue skies. The average value of the current is 2 picoampere. This one is the current density, 2 picoampere. Pico is 10 in the power of minus 12, yes, minus 12. So picoamps per square meter. So this is, let's say, an approximate or a brief scheme for the global electrical circuit, and we are using Ohm's law. So those of you are very, very familiar with this formula of the Ohm's law, but when I a little bit change it, I can get that the J is the current density, ampere per square meter. This is the electric field, and this one is the conductivity. This one is the resistivity. Okay? Voltage, current, resistivity, and I change it a little bit, and I get current density, electric field, and conductivity. So we have 10 years of electrical weather research. The ground station in Mitzpe Ramon, the ground station in the Hermon, this is how it should look like right now. And this is the first ground measurements of the electric field from low latitude and an arid low latitude. It's a desert site. Over here, this is a mountain site. So what we wanted to find is find the global and local impact of the diurnal EZ over annual, diurnal, and seasonal time scales. The last paper, no, this wasn't the last paper. The last paper will be the next slide. I just want to remind you that we measured the daily pattern or daily behavior of the electric field in fair weather only above Israel, and we compared it to the famous Carnegie curve. Carnegie curve was an experiment in the Pacific Ocean to study the behavior of the electric field, and it correlates almost fantastically with the lightning's distribution over the Earth. So this is the fair weather, and I spoke to it last year. What I wanted to present is the last paper that we published, Space Weather and Electric Field. So it just published, and it shows that space weather impact on ground level measurements is negative. We don't see any signature of space weather impact at latitude, the latitude of Israel, due to the dominant local effects, and I will speak of the local effects briefly. Why it's negligible? Because we have the strong magnetic shielding over here. So if there is an effect, it's below the detection threshold. The local impacts are very strong, so we don't see any effect of solar events. And we didn't took just simple events. We took the strongest event in the last 10 years. There was one in 2015 2015 and another one in 2018. This was a solar proton event, and the proton event was hitting Earth over here. And we see nothing. Nothing. This incredible increase in the electric field is only due to the increase of humidity. The humidity is affecting, and I will talk about it in the next slides. So we did like a factor separation. We measured everything. During the events, there were no clouds, there was no dust, because dust is increasing the electric field, and again I will show it in a minute. There was no rain, just high humidity, almost 90%. So this is the strong effect that we are seeing over here. But during the event, when it hit Earth, and we see the increase in the proton event, we see an increase in the electron event, nothing at all. Local impact of dust storms. So dust storms also affect by triboelectric processes. When dust particles collide with each other, they transfer charge. So charge accumulation is due to charging, according to dust advection, okay, when it passes through the station, because the particles interact with each other. So dust also affects the electric field. High humidity and fog. This is a paper that was published in 2022. Fog tends to increase the electric field since larger, slower, and heavy droplets cause a reduction in the mobility. If you are big, then you are moving slow. If you are moving slow, then the conductivity is decreasing. And if you are using Ohm's-law, when the conductivity is decreasing and the current density is constant, when this one is decreasing, the electric field should increase. So the decrease of conductivity results with an increase in the electric field, and this is something that we spotted when there is a generation of fog in Mitzpe Ramon during the autumn, typically. Then the electric field can rise up to several thousands volts per meter. So it has a strong effect. The clouds also have an effect. So this is the Ramon crater, Machtesh Ramon. And from time to time, there are clouds over here. And so these are low clouds. But there are times when you have alto clouds, medium clouds, and even high clouds. And this one we published again last year, the electric field variation caused by different layers of clouds. This variation during overcast conditions is due to columnar resistance by the cloud. The clouds are resistors. It's like you are putting a resistor in an electric field. It changes the current. Not sure if you remember, because the resistivity is proportional to the length of the coil and the surface area of the coil.
Cross section.
But we are not talking about coil, we are talking about how much? Somebody said something. We are not talking about the coil, we are talking about the cloud. So the length of the cloud and the surface area of the cloud. So this is a resistor. Clouds' resistivity will vary with depth and height of the cloud layer. Sometimes we have high cloud layer, like cirrus cloud, and we saw it in the past result of the Airborne campaign, almost 2 kilometers of high clouds. So clouds are a local impact. Typical magnitude of clouds impact of the electric field is hundreds kilovolt, hundreds volt per meter. We have also a topographic effect. So we measured on a mountain as well. This was published, I think, in 2017. And over here we see the diurnal behavior of the electric field. And in several mountains across the globe, including Mount Hermon. This one is the Carnegie file, the oceanic one. The Hermon is the black. This is the Hermon mountain. Okay, we have strong increase of potential gradient or electric field in the morning. We see it also in Davos mountain in Switzerland and on the other two mountains in Armenia. So the mountains have a strong effect in the morning hours. Why is that? At night, inversion layer trap the free charge in the valleys below the mountain, in the foot of the mountain. The charge attached to aerosols in what known as the electrode effect. So most of the charge is located at the foot of the mountain. Then solar heating destroys the inversion layer, and all the charge uplift, and the solar heating uplift the charge with the convection to the mountain tops. So a lot of charge that was accumulated the night before goes up to the mountain top. Again, a lot of charge lowers the conductivity, and with respect to Ohm's law, the electric field is increasing. This is, in German, is known as Austausch. So, we'll summarize. Besides that, our environment is an electrifying one, and we felt it in the last week. We have local impacts due to aerosols, topographic environment, dust, storms, clouds, fog, and also rain. I didn't show anything about rain because this is current work that we are doing in the group. Space weather and cosmic rays impact the upper atmosphere above Israel, but we do not detect any impact at ground level with an electric field meter. Okay? Current work and future plans in our electrical environment. So we want to find the impact of rain on the electric field, and we are seeing it's almost 10,000 of volts per meter because the rain washed the charge. And we wish to investigate the behavior of the electric field during Cyprus slow system, and later on with the Red Sea trough as well. Why? Maybe we can use another parameter to forecast and predict that will serve as a precursor for any extreme weather events. And so this is something that we are working right now with the staff. And it's we have very interesting results. Hopefully we will show it in the future as well. And that's all. I'm open for questions.
How sensitive are the measurements of the electric field to fog? I mean, to the depth of the fog and also to the extent of the fog?
You need everything.
Can you really say that you have fog, even if the fog is not very thick and it is only local?
What we detected about the fog, so the fog was on the station on Mitzvah Ramon, and later it backed into the crater. You know, if the fog is not there, then you will not detect it. Maybe you will have high values of humidity that will increase, but it will not increase the electric field like if the fog was on the station. So we need the fog to be on the station. Okay? Hopefully it answers.
Yes, it's up.
First of all, is it surprising that you don't detect on the ground flaring events or proton events that go into the atmosphere? So it's not very surprising.
So
the chemical interaction should be much higher with photons.
we have, there is a cosmic ray station on top of the Hermon, which can detect by several percentage, I think between 4 and 5 percentage decrease during the solar flare, and it's called a Furbush decrease, meaning that the cosmic rays are penetrating at a constant level to the cosmic ray station, so you get almost a constant level of ionization rate at ground level. And when you have a solar flare, then the magnetic fields of the sun prevent from the cosmic rays to penetrate into Earth. So then you get a decrease. And probably the technology of electric field is not sufficient enough and is below the detection level, the ground level. Because we measured it at 800 meters from Mitzvah Ramon and almost 2,000 meters in the Hermon, and we saw nothing. So,
Another question. So did you have any luck of sending a radio song during a flare event? Like to
No.
see the profile? Because I think we discussed this. We have now a model simulation of flaring events, and you see something of the sort, but if we had observation, of course, that would be
this is something that we wanted to do. We didn't succeed in doing it. You need a forecast of 2 to 3 days. You have a forecast of 2 to 3 days before the solar flare is reaching Earth, and it's something that can be done. But a lot of bureaucracy made it impossible for us to do it. Maybe in the future.
in the future.
Yeah, we can do it. Maybe you ask
Yeah, sure. So you showed interesting effects of the fog, electric field, or also of dust clouds. Is there an effect in the other direction? Does the electrical field affect the nucleation or the aggregation of dust in clouds or anything like that?
We didn't measure it. We had a station that was not operational, sadly, that was supposed to find the distribution and magnitude of the aerosols, but it didn't work. So this is something that we didn't do. We also wanted to investigate dust devils, because you have a lot of triboelectric processes in this one, but this is something that we want to do. So maybe we can do it together also. We just need the appropriate equipment.
Proposition.